Hello everyone, I welcome you to another video lesson. In this video, we'll look at how to do testing of hypothesis for problems based on the chi-square test. In the previous lesson, we looked at how to do the same thing for large samples using the z-test. For chi-square test, we'll introduce two different functions. One function where we compare observed frequencies with expected frequencies, and the other function where we do test based on the independence of attributes. So for these two, we have the functions chi_sq.test, which stands for the chi-square test. The first function takes as arguments the set of observed frequencies, the probabilities with which the expected frequencies are to be defined, and the rescale.p function. The rescale.p function ensures that the probabilities add up to give us 1. Or in other words, it checks whether we're doing it correctly or not. The probabilities that define the expected frequencies will change from problem to problem. We'll check that also. The second function uses the data, the given data, as the first argument. The second argument is based on the eighths correction. Now, if we wish to do the eighths correction, we define the value of the correct as true. Or in other words, if we do not wish to do the eighths correction, we give it as false. We use the same dollar function to calculate the p-value of the test statistic, and we do the comparison with the level of significance. We have already discussed solutions for chi-square test based questions in another video. I've given the link to this video lesson in the description. You can always check that. Today we'll focus on how to solve the problems using RStudio. First problem goes on like this. The table below shows the distribution of digits in the numbers chosen at random from a few pages of the telephone directory. The frequency of every digit is mentioned in the table, and we perform a significance. We perform a test to find out if the digits are distributed uniformly at the level of significance of 5%. So we define the null and alternate hypothesis. Null hypothesis says the data observed follows the expectation, or they are distributed uniformly. The alternate hypothesis says they are not distributed uniformly. So we define the observed frequencies at the first line. Observed is defined, the item observed is defined as C of. That's a vector. It contains all the 10 frequencies. And then we perform the chi-square test using the CHISQ.test function. So we pass the first argument as the observed frequencies. The expected frequencies are defined by this probability P is equal to REP of 1 by 10 comma 10. Now this is defined in this manner because we want the digits to be distributed frequently with the same frequency. Therefore, the probability that each digit shows up is the same. So we have the probability of 1 by 10 getting repeated 10 times. So the total of the frequencies is divided by 10, and that is used to calculate the expected frequencies. And we ensure that the probabilities add up to 1 by using the rescale.p is equal to true part of the function. And we calculate the p-value of the test statistic and compare with the level of significance at 5%. And having defined all this, let's find out how the execution happens using the RStudio software. So we have the vector defining the observed frequencies. We have the value of the test statistic defined by the CHISQ.test function. And we calculate the p-value. And based on the p-value, we will arrive at the decision. I'm running this chunk and let's find out the result. The chi-square test, the value of the chi-square test happens to be 0.676 with a p-value of 0.99. The 0.99, as we know, is greater than 0.05, the level of significance. And therefore, we cannot reject the null hypothesis. And therefore, the die is fair. The null hypothesis must be accepted, and we have arrived at the conclusion. We go to the next problem. The next problem is based on the Gregor-Mendel experiment, where the seeds are distributed in the ratio 9:3 to 3:1. That was theory. We compare this with for a sample of 800 seeds, at 1% level of significance. Therefore, we define the null hypothesis that the experiment supports the theory and the alternate hypothesis which does not support the theory. So we define the observed frequencies in the very first line and we calculate the proportions. Now, since the proportions are different here, we take a step to define that properly. We first total all the observed frequencies and we get the proportions defined as 9 divided by the sum of 9 plus 3 plus 3 plus 1. That's the proportion for the first class, 9 by 16, followed by 3 by 16, 3 by 16, and 1 by 16. We pass these as arguments into the CHISQ.test function, and we compare the p-value that we obtain with the level of significance alpha. Having written the code, let's find out what happens when we execute the same using RStudio. So here again, the observed frequencies are defined, the expected frequencies proportions are defined, the comparison rule is defined, and let's run and check out what happens. The chi-squared value obtained is 0.866. The degree of freedom is at 3. The p-value is 0.8345. We know that the level of significance is 0.01. So comparing 0.8345 and 0.01, we see that it's greater, and therefore the null hypothesis must be accepted. And as a result, we conclude that the experiment in fact matches the theory. H naught is accepted. We go to the next problem, which is based on a contingency table. A survey was conducted across 200 youngsters to find out if their attributes of employment nature and the place of residence are associated. We use a 1% level of significance to test this claim, and we'll do this. So for null hypothesis, the attributes are independent. The alternate hypothesis says they are not independent. Now, this is a slightly different procedure because the data is presented in the form of a contingency table. So we define that as a matrix. So it's a matrix which has two rows, and the entries of the matrix are defined row wise, and this is assigned to the item data. So for a contingency table, the function is slightly different. The CHISQ.test function takes in only two arguments. Argument number one is the matrix representation of the observed frequencies. Argument number two is whether we need to perform the eighth correction or not. In this case, we see that all frequencies are greater than 10. Therefore, eighth correction is not necessary. Therefore, we pass the value of the correct value as false. So we calculate the p-value and we do the comparison with the level of significance at alpha. Right, now having written the code, let's just run this code in RStudio and find out what happens to the output. We have defined the vector containing the observed frequencies in the form of the matrix. We have set the value for the eighth correction to false, and we have defined the rule for the acceptance and the rejection of null hypothesis. Now we are ready to run the code. Let's run the code now. The output of the code tells us that the value of chi-squared is at 37.121. It also returns the expected frequencies. The p-value comes down to a very small number compared to the level of significance. And since p-value is less than alpha, we reject the null hypothesis. The attributes are not independent, or we conclude that there is an association between the nature of employment and the place of residence. We move on to the last problem, the chi-squared. This problem discusses the fitting of a binomial distribution to the given data. 5 dice were thrown 243 times. The number of times the numbers 3 or 4 showed up is given in the form of table. We examine to check if the dice are unbiased at 5% level of significance. So we first define the observed frequencies at 30, 72, 74, 51, 14, and 2 using the vector C. We observe that one of those frequencies is less than 10, and hence we club the last two. So we pass the new set of observed frequencies as R observed, where the last two frequencies are clubbed. And because this problem follows the binomial distribution, because the outcome could be either 3 or 4, or it could not be 3 or 4. So the two-way outcome defines the binomial distribution aspect. and we do that using the binom function. You can recall before in a video lesson for R studio using like probability distributions, we define the binom function. Therefore, we calculate the probabilities, multiply with the total of all the observed frequencies to return the expected frequencies. Like we did for observed frequencies, we also add the last two values for expected frequencies because one of them is found to be less than 10. Having found both these sets of frequencies, we pass them as argument to the CHISQ.test function, and we also set the R rescale.p to be true. Based on the p value, we compare that with the value of alpha, and we define the rule for accepting or rejecting the null hypothesis. Rejection means that the dies are not unbiased. Accepting means that the dies are in fact unbiased. So having done the coding, let's find out what happens to the output. So as usual, the observed frequencies are passed in the form of a vector. They are refined as R observed. We calculate the expected frequencies using the d binom function and multiplying the probabilities by the total of all observed frequencies. We define the rule for the decision making. We see that the value of chi-squared comes down to 6.627 and its corresponding p-value is 0.15. Now, this 0.15 is greater than the level of significance, which is 0.05. And because it is greater than alpha, we cannot reject the null hypothesis. Therefore, H naught is accepted. Dies are unbiased. That gives us a very clear understanding of how to do testing of hypothesis based on chi-square test using the R studio. I'll meet you very soon with another video lesson.